Well, so I think it's now the time, and maybe some more people will join later to the session, but it's time to begin. So let's start with the second training session with Professor Venkatesh from BITS Pilani. And this second session will be 2 hours, and it's about the microsystems design. So Professor Venkatesh, you can begin with this.
Thanks, Carlos. Okay, in the previous session, good afternoon and good evening to whoever has joined, depending upon the time zone you are in. So today's session, the previous session, we have introduced you to the topic of MEMS and DEMS, and we have discussed about the scaling factors and all of that. So, and I also discussed about the process value chain in the development of any of the micro or nanoscale systems under consideration. Once you look at the process value chain, the first and the fundamental thing what you saw there was the design, right? So, and after the design, we went ahead for the fabrication, next to the characterization, followed by the packaging. Now, the first phase over there was the design. So, in the today's session, we will go ahead with the how to go about designing a micro machine devices and their consideration. That's basically a microsystem design. Just a second. Giving some trouble. PowerPoint is giving you trouble. Maybe share it again. Okay. Yeah. No, it's better. Okay. The first process is the design of the microsystem under consideration. Now, when we discussed in the previous session, we said one can realize any of the micro machine devices with the silicon, polysilicon, or germanium, any of the semiconductors under consideration. So the majority of the things, even if you process what you will be following for the fabrication of your devices, they are all again silicon-based sensors. So as to make up any of the silicon, first and the fundamental thing is that we need the single crystal silicon wafer. So as to have the wafer fabrication, we will basically go by the CZ method under consideration. We will go into the details of it whenever we go to the fabrication. So as to go get the seeds as a silicon, the single crystal silicon seed, we go forward for the CZ method, and with the help of which either we want, you can go with the 4-inch wafer or 6-inch wafer, or you can even go with the 8-inch wafer as well, or even the 12-inch wafer also. Depending upon the diameter, even the thickness of the wafers will also vary. This is 500 micrometers, it won't be millimeters, 750 micrometers, and this is 1000 micrometers, right? And as we looked into, right, in the previous session, we discussed on there are several orientation of the single crystal silicon. Either it can be 100 wafer, 110 wafer, or 111 wafers. They are again decided by the orientation of the wafer is basically decided by the Miller indices. The Miller indices will be, let us say that if you take up any of the normal planes under consideration, the indeed will intercept the x-axis at unity. This is basically a single unit cell. All the dimensions are unity, right? So it will intercept the x-axis at 1 and y-axis at infinity and the z-axis at infinity. So if you take up the three, then so it will be 1 infinite, and if you take up the reciprocal of them, you indeed will get 100. So that's how we usually, whenever you take up a normal planes under consideration, you will get a 100 family of uh, planes. On the other hand, if you take up any of the diagonal planes, it will intercept x-axis at unity, y-axis at unity, and z-axis at infinity. you will get a 110 orientation along the diagonal planes. Similarly, whenever you take up an inclined plane, that's a body diagonal under control. Whenever you take it up, then you will get a, if you take up an inclined plane, you basically get triangular orientation. So as to look into the what is the Miller indices for the respective direction, as I already told you here, right? You need to first look at the intercept along the different orientation and take the reciprocal of it, then normalize the entire thing. Then you will get the Miller indices. Now, whenever we want to look at any of the microsystem under consideration, the microsystems are completely a coupled system. Any of the MEMS devices or MEMS devices, they are completely coupled. We have the electrical physics, we do have the mechanical physics associated with it. Now, as we said, it's a completely electromechanical system. So first let us start from the mechanical system and let us bring in the marriage to the electrical system. Right? Now, if you look at from the basic of the mechanics, the first and the fundamental thing comes from the mechanics would be that what's the stress strain relationship? To take up an unloaded rod, let us say this is the initial state, right? And if you apply a load onto this, and if you take up a small element over here, right? Indeed, each and individual material point will experience the amount of force, right? So the whatever is the internal stress which gets generated within the material will be given by force divided by the cross-sectional area subject to constant. It's a normal stress, right? And on the other hand, whenever you apply a load, it's not only the stress gets induced, because the stress induced, there will be strains which get, there will be elongation of it, the change in length by the original length will be the strain induced in material, right? So if you look into, there is not only the elongation, there will be reduction in the cross section as well, right? So there will be lateral strain and there is a linear strain. Ratio of lateral strain to linear strain is basically the Poisson's ratio. Now, on the other hand, if you take up any material, right? If you take up this box, and let's say if you are fixing it from the top, if you're basically piling up a sheet of papers, and if you apply a load from the top, then what will happen? It will indeed will shear this, right? So there will be a shear. So the shear force is basically a shear force acting on this divided by the shear area will basically give you the shear stress induced in the material. Right? So as I basically told you, we do have the normal stresses, which is represented by sigma, and then the shear stress, which is represented by tau. Tau is basically the shear force divided by the shear area. Now, at the same time, right, if you look at this here, so we will get the shear stresses, but if you look at this, we do have what? At the same time, this is the initial position. And upon deformation, then there is a change of delta x over here. And this is my L. So if you take up the, if this is the amount of angular deformation what I get, if I take up tan theta, then I will basically get delta x over L, right? So that is basically for a small amplitude deformation, tan theta will be approximately will be equals to theta, then shear strain comes out to be equals to by delta x over L, right? And if you take up the normal stress and normal strain, if I go back to the previous slide, whatever I had described over here is basically a normal stress and normal strain. The ratio, if you look at it, if you draw the stress strain curve, then you can see that on the initial regime, this normal stress and normal strain will indeed be straight line, and the what we can see that stress is proportional to strain within the elastic limit, and the proportionality constant is basically the elastic modulus or the Young's modulus under consideration. If you take up a polysilicon under consideration, then typically the elastic modulus will be around 160 GPa. On the other hand, if you take up a 100 orientation of silicon, it will be around 130 GPa. On the other hand, if you take up around 110 orientation, it will go even to 190 GPa. Right? So depending upon the crystallographic orientation, since the atomic packing factor will also change, so you also even your value of elastic modulus will also change. So here I basically explained you with respect to the elastic modulus. Now you look at it, whenever you apply a shear force onto the system, then the shear stresses get induced. The ratio of shear stress to shear strain is basically the shear modulus G. And there's an interrelationship between this E and G, which is basically E is equals to 2G times 1 plus nu. Right? The same thing is has been represented that G is equal to E divided by 2 times 1 plus nu. Right? So this is basically a typical stress strain curve, what you will get out for any of the elastic material. For example, any of the ductile material like aluminum or even if you take up for steel, this is how the typical stress strain curve comes out. Here you can see that till the proportional limit, it indeed is a straight line. And if you take up a different materials, you do get a different stress strain curve. If you take up a brittle material, if you take up that for a silicon under consideration, this could be the typical stress strain curve, what you get it out. If you take up that for steel, this out you will typically get out. On the other hand, if you take any of the soft elastomeric material or a hyperelastic material, you do get it out a stress strain curve like this. For example, even for a rubber, I would say that you will get a stress strain curve something out like this rather than this, right? So for the rubber, you will typically get a stress strain curve like this. So you can see that for single crystal silicon is actually having far better, much stronger than that of the stainless steel. Now, I mentioned that stress is proportional to strain, and we get that to be the modulus of elasticity. That is basically by taking into account of uniaxial elongation under consideration. Right now, whenever you take up a material, you apply a load, what happens? There is not only elongation in this direction, at the same time, there is a contraction in the other direction. So what does that mean? So if I am going to take up a small element inside this, that element, the small element inside this is indeed experiencing stresses in this direction as well, and even the stresses in the orthogonal directions to it, right? Since it experiences stresses in all three directions, that's why we indeed get the contraction of the element in the other directions. So the same thing you can see here is not only the stresses you get it along the x direction, because the Poisson effect, you do get the stresses in the other direction as well. And it is not just that it is getting the normal stresses, it also subjected to the shear stresses, right? So the shear stresses are basically represented by tau Ij, where I is basically along a which plane. For example, it's along the x plane, along the y direction, that is basically the chip, right? So we are the first I corresponds to the plane and J corresponds to the direction. For example, if you look at this here, this is my x plane. If the normal to this plane is basically the x direction, right? So this is my x plane under consideration. Tau on the x plane in the y direction is given by tau xy. Similarly, tau in the x plane in the z direction is given by tau xz, right? So similarly, we do get along the y plane, this is my y plane and this is z plane. Any plane under consideration is indeed dictated by the normal to the plane, right? So the normal to this plane is basically y, so you will get tau y in the z direction and tau y in the x direction. So if you look into what we basically get, we get sigma xx, sigma yy, sigma zz, and I will get what? Tau xy, tau yz, tau zx, and I do have tau yx, tau zy, and then tau xz, right? Now, if you look into what exactly you can see the similarity between these two, is that is just x and y has interchanged the position. So that's what we say tau xy is equals to tau yx. So which is basically is called the cross shear, right? And we can say, we can even well derive that cross shears are always equal. So that's how we basically get into if the 6 component of stresses, 3 normal stress components, and 3 shear stress components. So these are basically T1, T2, T3 till T6. These are basically the stress vector. The T1, T2, T3 are basically the normal stresses, and T4, T5, T6 are basically the shear stresses. So you can see that this is basically a 6 by 1 vector. And similarly, here you will be having 3 normal strain components and 3 shear strain components. So you will again have a 6 by 1 vector. And whenever you take a 3-dimensional state of stress, then this will become a 6 by 6 matrix. So as we know that since it basically dictate, indeed will be the elasticity of your material, we indeed call it as matrix of elasticity coefficient, or since the elasticity indeed dictates what the stiffness of the material, that's why we do even call it the stiffness matrix. And if you take up the inverse of this we can write it out as what? The sigma to be equals to my C matrix times your epsilon, right? This C being the stiffness matrix, and if you take up C onto the other side, then what we can write? So, sorry, then the same thing, I can basically write it out to be epsilon to be equals to my C inverse, which is basically represented by the compliance matrix times sigma. The same thing has been written over here. So epsilon matrix is compliance matrix times the your stress vector. Whereas is basically a matrix of compliance coefficient. Now we can say even derive that when C indeed will be a function of your elastic modulus and the Poisson's ratio. If you know the values of elastic modulus and Poisson's ratio, you can even well populate the complete C matrix for 100 direction. For example, the elastic modulus along the 100 direction will be somewhere around 130 gigapascals. On the other hand, Poisson's ratio, you can take it to be around 0.3, and you can populate the complete C matrix under consideration. And whenever you take up any of the microscale structures under consideration, you can come across several boundary conditions. Either they can be made out of beams, right? So there can be several boundary conditions associated with it. For example, it can be a completely fixed support, or also we can have a one is that we can have completely fixed support like this. For example, just like a simple cantilever beam, or we can have a proof mass suspended with the help of a beams, then proof mass indeed will guide it. So this will become a guided support under consideration. When it is a fixed support, then it can neither undergo translations nor undergo rotation, right? So it has 0 translated degrees of freedom and it has 0 rotational degrees of freedom. On the other hand, if it's a guided support, then what happens? Then it is allowed to translate, but it can't rotate at the guided support. On the other hand, if it is a free end, then it can undergo translation in the two directions, but it can't undergo the rotations. So then one can get several boundary conditions associated with it. And then whenever you take up, we do come across plenty of beams. The beams suspended, the proof mass suspended with the help of set of beams in several configurations, whether you take up a microphone, accelerometers, or gyros. In scientific applications, you do get these beams under consideration. So let us look into what will be the stresses induced in the beam and other thing. So whenever you take up a beam and if you apply a load on this, right? For example, you take up a cantilever beam. If you apply a load, if I take up any cross section under consideration, so we do have the moments which will be there on the respective cross section. This is basically a one cross section I have taken it up. Whenever there are moments, then indeed we will get the stress induced in the beam will be given by My by I, where M being the moment and y is the distance above the neutral fiber. The neutral fiber is the one ST which has been made. The neutral fiber, if you look at this figure carefully, this is my initial position, and after we bend it, what happens? The top fibers have undergone the compression and bottom fibers have undergone the tension. You can see that there is a elongation of the bottom fibers and there is a compression of the top fibers. So there is a stress gradient from top to bottom. And you can see one set of layers wherein there is neither compression nor elongation. And these fibers are basically what is called the neutral fiber. Right. So the neutral fibers will neither undergo elongation nor undergo tension. Right, and this plane is also called the neutral plane. And the whatever is the why you can see here the expression in the expression for the stress. If I take up any section in this, just a distance y above the neutral plane, the distance above. If you will take up the cross section of this, the cross section could be a rectangular cross section. Majority of the MEMS devices, we can come across a rectangular cross section. If this is my neutral axis, the distance above the neutral axis is basically the y, right? So the y being the distance above the neutral fiber and I is basically a moment of inertia. And we can see if I take up the top fiber or the bottom fiber, since T is the thickness, then T by 2 is the distance above the neutral fiber. So that's how we can see that the maximum stress induced will be MT by 2R. And one can evaluate what will be the deflection of the beam. Let us see that if I apply a load, we can see that for a simple cantilever under consideration, we do get maximum angular deformation to be FL squared divided by 2EI. All of them you can even well derive it with the help of the Euler's relation, which basically comes out to be EID square by dx square to be equals to mx, right? And from this, you can just define y of x. But after defining the y of x, you need to put it up over here because as we can see that this is basically a y at this point, this is a deflection at this point. And you can see that the deflection indeed is a function of the distance x, right? The length, the x under consideration. That's why we basically say y indeed will be a function of x. So first we need to define y as a function of x and then put it over here. And from there you can evaluate what is the value of maximum deflection and what is the value of maximum slope is the structure, right? For a given force under consideration. Now, at the same time, if you take the difficulties of a guided cantilever under consideration, then what happens? Then you will get maximum deformation with the force F to be FL cube divided by 12EI. And if you take up any element and if you want to represent it out as an elastic spring, right? If I want to represent it as an elastic spring, what does an elastic spring basically say? Whenever I apply a load F, if K is the spring constant, K is a spring constant. If I take up anything, right? For example, I am going to take this up, take this steel, right? This will give you a better one. This is basically a steel rod. Now I am going to apply a load. Then what happens? There is a deflection, correct? So whenever I apply a load, then there is a deflection delta of this, right? So the force is directly proportional to the deflection, and this proportionality constant is basically the stiffness of the structure, right? So if you look at this, for simple cantilever, we have FL cube divided by 3EI. So on the other hand, I can write the stiffness to be equals to force divided by this delta, right? So the maximum deflection, what I got is this. From this, if I write the expression for the stiffness over here, we can see that this comes out to be 3EI over L cube for the cantilever, which basically comes by force divided by deflection. On the other hand, If I write the stiffness for a guided cantilever, we can see that this comes out to be 12 pi over L2, right? Now, on the other hand, now think of what would happen if I am going to support it from both the sides. Note that length is the same across all three of them. So if it is a fixed beam, then we know that indeed we get a maximum deformation at the center. So the maximum deformation, what we get it out will be FL cube divided by 192i. Now we can see that we get maximum, the stiffness, if I evaluate, I can get it out to be F192EI divided by L2, right? Now, you compare between these three cases, a simple cantilever, guided cantilever, and a fixed beam, right? And you tell me which one is having more stiffness, either a fixed beam, or a simple cantilever, or a guided cantilever. Which one is having more stiffness? We can see that the fixed beam has more stiffness. Why is it so? Whenever I am going to constrain it from both the sides, naturally, what I am not letting it to either rotate or translate at into both the ends. So naturally, the stiffness of the structure will shoot up, right? So we can see that the fixed beam has more stiffness. K for fixed beam is much larger than that for a guided cantilever, which is greater than the stiffness of a simple cantilever, right? So the same thing we can basically written over here, right? The stiffness is basically given by force divided by the deformation that I already explained. Under a zero load, this is the position. If I apply a load, if I get a deformation X, then I can write it up like this. Now, on the other hand, one can even let's say that if I am going to connect two springs in parallel, then what happens? If I apply a load F onto this, then at this point, we know that this is having just like I am having one is aluminium, other one with the steel. Each one will be having what? The different values of what would happen here? Will the deformation be same or will the deformation be same or will you get the same force between the two? What would happen in this case? In this case, if you look into the force will get distributed between both of them. One is K1, other one is you will get F2. So you will get F2 equals to F1 plus F2. But the deformation remains. It's just like what you have it out is in composite beam, right? We know that if I am going to represent it out to be with K, with a equivalent system like this, then I will get F to be equals to K delta, which is to be equals to K1 delta plus K2 delta. Then we can see that this delta will basically cancel out. When they are in parallel, then I can see that the effective stiffness will be much more than the individual stiffnesses under consideration. Similarly, on the other hand, if I am going to connect them in a series combination, let us say this is K1, other one is K2, then I can even well come up with an expression that the what in this case the deflection of this is different at this point will be different, deflection at this point will be different. The total deflection will be delta 1 plus delta 2. That's how we can even well come up with 1 by k to be equals to 1 by k1 plus 1 by k2. What does that mean? In general, if I have any n number of springs in parallel, then K effective will be equals to summation of I ranging from 1 to n Ki. On the other hand, if they are connected in series, then it will be 1 over K effective will be equals to summation I ranging from 1 to n, 1 over Ki, right? So in general, this is what is the expression, right? Now, what do you mean? I mean to say that if at all we are connecting the springs in series, the effective stiffness of your system will be much smaller than the individual spring. Right now, we can see that here I have several beams which are on the same substrate. Right now, we have two cantilevers. One is A, other one is B. The both are of same length, same width, and of same thickness. Now, in one case, I applied a load from the side, other one I applied a load from the top. Then what would happen? Which one is undergo more deformation? Either A will undergo more deformation or B will undergo more deformation. Which one would undergo more deformation? If you look at this carefully, see this, if you take up your scale, you can apply a load from the top, you can easily bend. On the other hand, if you apply it from the side, you can't so easily bend. Why is it so? Because the sectional inertia from the side will be quite large in comparison to that from the top. If you look at it from this figure as well, here you can see that the thickness is quite small in comparison to the width. Since width is larger than the thickness, your WT cube divided by 12 is of course much less than TW cube divided by 12, right? This is what you get the sectional inertia, the TW cube divided by 12, the moment of inertia for this section. On the other hand, for this, I will basically get WT cube divided by 12. Since the moment of inertia are different, then naturally we can see that we can easily bend the second case in comparison to the first one. That's why we can see that stiffness in the y direction will be much smaller than the stiffness in the x direction. Now, if you take it the same thing, instead of having a simple cantilever like this, what I will do is that I will make use of a meandering structure like this. So typically, whenever we want to reduce the stiffness of the structures, then we can make use of this meandering. So it is like having two springs in parallel. Right, we already know what is the stiffness of an individual cantilever, which is around 3 by L3. This is like I have two cantilevers in series, so the effective stiffness comes out to be 1 over I that you need to evaluate. Right, so we can see that whenever we will go forward for a meandering structure, so naturally the overall stiffness of the structure will further come down. And here also, just like your A and B, here I have D and E. Now, look at this carefully. In this case, thickness is much larger than the width. Correct? Since thickness is much larger than the width, then you can actually, this is a case of a plate, you can see that if I apply a load from the side, since the width is much smaller, I can easily bend from the side in contrast to that from the top. Agree? So one can evaluate it by making use of this by 3 by L cube. You can evaluate this. I is basically WT cube by 12 for this. In this case, it is TW cube divided by 12. Now, the similar case, instead of having it to be around, let's say that I want to increase the length of this. So let's say that I want to put it into few meters. So in that case, I can't have a meter length cantilever and make it out in a micro scale. That would be very, very difficult, and also that is not justifiable. And that's why we indeed go forward for if at all we want to reduce the stiffness, we would like to go forward for the meandering structures under consideration. This is a similar thing what I told you about this case. In this case, we had a load from the top. In this case, we are having a load from the side. And till now, I was mentioning you about a series combination. In this case, this is basically AFM cantilever. You can see that I have two cantilevers which are attached together, and I have applied a load. The tip deformation of both of them are the same. This is a case of a parallel combination of both of them, right? So in this case, the overall stiffness comes out to you need to evaluate stiffness K1, you need to evaluate stiffness K2. Sum of together will get the overall stiffness of this. Right? Now, on the other hand, whenever you take a majority of the micro structures under consideration, you do have proof mass suspended with the help of set of beams. Where proof mass suspended with the help of set of beams. This is basically a proof mass suspended with the help of set of beams, and it's indeed anchored onto the substrate over here like this, right? Now, since we have a proof mass, and if I'm going to take up a section of this, we can see that this is basically a fixed end. Here I have a plate. If I apply a load F onto this, then we can see that this is actually, since it's a fixed end, there will be a zero translations and rotations. Since I have a proof mass over here, this indeed will guide the beam. That's why it comes out to be a guided support at this end. So one end you will get a fixed end and the other one will be a guided support. So this will be a case of a guided cantilever under consideration. For a guided cantilever, we have already obtained the stiffness to be 12 EI over L2, right? Now, if you take up the first case, we have one guided cantilever, first guided cantilever, and the second guided cantilever, and both of them are basically connected in a parallel combination. Look at this, they are basically attached to the same plate. They have the same deformation delta. The tip deformation is the same for both of them. So it will further sum up, which will come out to be what? 12 EI by L cube. If you take it up, I will be WT cube divided by 12. So this 12 and 12 will cancel out. That's how we will basically get it out to be ETW2 divided by L, right? Now, on the other hand, this is a case of an accelerometer, and this first one is a case of a micrometer, and the second one would be a case of an accelerometer or even the microphone under consideration, wherein we have a proof mass suspended with the help of a set of beams. Here we also get a fixed end over here. This is basically a fixed support, and this side will be a guided end under consideration. That's how we indeed get it out as a guided cantilever. How many guided cantilevers are there? We are totally 4 guided cantilevers. So the effective stiffness in this case comes out to be 4 times EWT cube divided by M cube. Now, in some cases, there could be even the torsional motion as well. If at all there is a torsional motion, then you can apply even T by J to be equals to tau by R to be equals to G theta by L. Then you can come out to be, if I am going to club both of them, one can get the maximum shear which gets induced will be equals to TR by J, where J is basically a polar moment of inertia given by half of pi r to the power of 4. Right? And whenever you fabricate the structures, there can be impedance stresses which are inherent during the fabrication. Right? So whenever you do the fabrication, you will take it up to the elevated temperature, you will bring it back to the room temperature. During the process, the internal stresses get developed during, right? And because since they are unwanted stresses, it comes up from the fabrication. That's the residue of the fabrication. That's why we also call it the residual stresses are induced, depending upon whether you have a tensile stresses or compressive stresses. Either the structures will either curl up or it will curl down. You can see that the structures are basically curled up, and you can see the stress gradient. Because the stress gradient, the structures are basically curling up. And how can we say whether it's a tensile stresses or compressive stresses? For example, you can take up a sheet of paper. You can take up a sheet of paper, and what happens? You are having it on a substrate. Now, if I am going to apply a tensile stress onto it, then what happens? It will further undergo, it will basically flatten out, right? On the other hand, you apply a compressive force, then what happens? It will undergo wrinkling, right? So, that's how you can get it out. You're facing a simple feel of how the film will get a tensor stresses or compressive stresses. For example, let us say that this is my substrate material and this is my deposited material. And the substrate material is in a zero stress and a deposited material is having a tensile stresses in it. If at all tensile stresses are there, so as to relieve the stresses, then what happens? Then it would further bend up. On the other hand, if at all it has a compressive stresses induced in it, then indeed, so as to relieve the stresses in it, it indeed will curl down. Now, as I told you, if at all, the deposited material has a tensile stresses, it will further curl up. Now, let us say that I want to reduce this curling of it. What you can do is that you can further deposit another material which can induce a compressive stresses, and you can even make the flattening of your devices. And there are plenty of things you can get it out in the mechanical design of your micro resonators under consideration. The first and the fundamental thing will be the force constant. The force constant will basically tell us which is basically I told you about the stiffness, right? The stiffness will basically tells me how good is the flexibility of the device under consideration. And it's very, very important either you take up a static MEMS device or if you take up a MEMS dynamic MEMS device. In both the cases, the stiffness plays a very, very important role. And if you take up on the other hand, the dynamic MEMS devices, as the name itself indicates, the resonant the dynamic, which keeps on changing with time. So in that case, the resonant frequencies will play an important role. So omega n is basically given by square root of cable gap. Here you can see it's basically as a function of the given load, right? If I am going to take up any structure and if I'm going to apply an harmonic load onto this, and I will measure the deformation of the structure, and we can see that at one particular frequency, the amplitude of vibration will further go up, and that's basically the resonant frequency, right? So the resonant frequency is also given by square root of k over gain. Experimentally, one can figure out by the peak picking approach. Now, whenever you take up any of the electromechanical resonators under consideration, uh, when right here in the for a simple case, you can take like a proof mass suspended with the help of set of beams, and I have a bottom electrode below this, and I'm going to apply a potential between the top and the bottom. I'm going to apply a potential between the top and the bottom. If I apply a potential between the top and the bottom, then what happens? There exists an electric field because of the applied potential, right? So when there is an electric field, then there is an electrostatic force, right? Which is basically Fe, the F electric. Now, since it is the structure is indeed is suspended with the help of beams, right? The beams want to restore it back to the equilibrium position, right? So there is a mechanical force which basically comes from the springs. So that is basically the spring constant times the deformation. So there is always a tug of war which is taking place between the electrical forces and the mechanical forces. Sorry. There's a tug of war taking place between the electrical forces and the mechanical forces, depending upon the which one will be large, right? Either the mechanical forces are large or the electrical forces are large, then if at all at a particular voltage, we can see that the electrical forces will overtake the mechanical forces, and indeed it will lead to a phenomena of pulling. So I will come to that phenomena of pulling very shortly. Right now, what are the different electromechanical analysis you can think of? Given that for this, you may need to, given the force constant and suspensions, you may need to evaluate the full lane, and then may need to design the dimensions and other things for the applied voltage. This is what you may need to do it. So you need to come out with the design for your structures depending upon the application, and then given the mechanical parameters, including the force constant and the resonant frequencies, you may need to come out with the complete design, and then you need to come out with the complete layout of it. Now, what are the different analysis you can get out for the forces? Either it could be a fixed free, you can get it out, right? So I already told you this, so I'll just skip this as a matter of time. Either you can get plenty of things. Either I can have a fixed free case, or I can, this is basically a guided cantilever case. There are 2 guided cantilever case. We have 4 guided cantilever case. This is like 4 times the stiffness of a single guided cantilever. This 2 times the stiffness of a single guided cantilever. It's just a simple guided cantilever what we get, right? So these are the microfabricated structures what we can see. This is basically a fixed beam. This one can realize it quite easily using your SOI process also. And these are basically a cantilever beams, which are again can be realized with your SOI process. This is again a cantilever plate. This also can be realized with the whatever the process we will be following. And I was telling you in the earlier case, right? Let's say that if you want a larger length of the beam, then in that case, we indeed go forward for serpentine beams in the consideration. You can even realize the serpentine structures also with the help of SOI process. There are several boundary conditions you can get it out. As we know that for any given boundary conditions, we have 6 degrees of freedom, 3 translations, and 3 rotations, right? So if at all it's a fixed conditions, then it is 0 translations, 0 rotations. On the free end, it is capable of undergoing both translations and rotations. Whereas in the case of guided support, it is capable of translation but not rotation, right? And this is a case of a clamped beam. And note that here these are basically what you can see there. This is basically a beam, and this is another beam. And here I have basically a beam, right? And this can be even well used in a micro mirror application as well, right? And this is basically from the CNRS lab. So each one of them is basically a guided cantilever. So stiffness comes out to be 2 times the stiffness of individual beams. Whenever you are doing the mathematical evaluation, please do take care of the things carefully. And this is a case of a micro machined accelerometer, right? So this is, I have a proof mass, I have a larger bulky proof mass suspended with the help of beam. You can see the structure over here, right? So this is a complete single accelerometer under consideration, and this is a simple single seal. You can see the dimension of your silicon accelerometer, and then even in a single seed under consideration, single package seed, it's as good as a dimension of single package. The entire chip altogether will be hardly in the range of around 3 centimeters under consideration. Whenever you pick up any of the MEMS devices under consideration, if at all you are going by the surface micro machining process, in your case, we are not going by surface micro machining process. We are going by the SOI process. If at all you are realizing by surface micro machining, I would recommend that you do understand that as well. You can realize the things by surface micro machining, or you can realize by the SOI process also. Now, if you are realizing by surface micro machining, then one can get the bottom electrode below this. On the other hand, with your process, note that you are not going to get any bottom electrode. You are going to have, I'll just explain that whenever you go forward for your fabrication session. In your process, in the SOI process, you don't get bottom electrode. Please don't design any of your structures wherein you have a bottom electrode in it. Okay, I will tell you what will be the other ways you can go ahead and design the capacitive-based sensors. If at all we are going by the surface micromachining, let us say, then we can have the bottom electrode. And let's say that if I apply a load F, then indeed we get a capacitance change between the top and the bottom, right? Or you can even well optically measure also. One can have the optical reload as well. That also can be done. Now, for example, what would be a typical force constant of a fixed free beam? So you know that if I apply a load, yes, you know that for a simple cantilever, it will be 3 EI by L cube. So if you know the dimensions and the material properties, you can evaluate. So if you take up any of the materials, whether you want to go for a single crystal silicon or polysilicon, you can easily get the material properties using the MEMS clearing house. You can just go to MEMS clearing house and you can get the material properties of the for different layers, all of them, you can get it out over there. In there, if you go to MEMS clearing house, please go there and check it out. What are if I go to the SOI process? What are the material properties of each and individual materials? Please do make a note of it. Whenever you have taken any of the micro scale structures under consideration, right? If let's say that usually we do get a small deformations under consideration. Typically, right? Let's for example, whenever the end deformation is around 10 to 20 times, is less than 10 to 20 times. Next, indeed, it's called a small deformation. In around 90% of the cases, we get around in the small deformation range because as we know that as long as it's a small amplitude deformation, your linear theory will go through and you can go forward for a completely analytical solution of it. On the other hand, if the amplitude of deformations are very, very large, then the nonlinearities will further kick in. If the nonlinearities kick in into the system, then you need to go forward for the FEA-based approach for this. Right? And also, it's not just that I need to go for FEA-based approach. You can even well solve it analytically as well, but it is bit time consuming, nothing much. But you need to have some more training with it. First do the analytical things, right? That can still be done. But I would recommend you can go with the FEA-based approach if at all it's a large amplitude deformation under consideration. So this is an important slide for all of you that whenever you take up any of the beams under consideration, the first and the fundamental things are this. For the simple cantilever, the vertical deformation, what you get out will be this. And then that of the natural frequency associated with the simple cantilever will be around 3.5 divided by 2 pi EI divided by rho AL to the power of 4. This is a fundamental natural frequency, what you get it out. And I also told you that whenever we want to have a larger length under consideration, you can't make a large pillar like this and you can't go ahead with this. Rather than so as to save the chip real estate, we indeed go forward for the meandering beams. So meandering beams will actually save the real estate of the chip. It's not that it's only your design will be there in the entire 6-inch wafer. Even the other design should be accommodated over there, right? Indeed, if your length is quite large, so better you go forward for the meandering beams or the zigzag beams under consideration. So these are some of the examples where you can see that indeed we are going forward for a meandering beams. Only this much is 500 micrometers. Since they are quite larger beams under consideration, we indeed go forward for zigzag beams or the meandering beams under consideration. This is the case of an AFM cantilever, right? And the order of the resonance. Now, earlier I said natural frequency for any system is square root of k over gamma, right? So, whenever you excite any structure under consideration, let's say that you disturb the system and leave it, so all the vibration, all the modes of vibration will kick in. For example, if you take up a simple cantilever, and if you just apply a static load, then what happens? It will just undergo deformation and stay at there, right? Now, on the other hand, now I will apply a sinusoidal load. If I apply a sinusoidal load, then what happens? Then it will basically vibrate about its equilibrium position. Correct? Now what I will do is that now I am going to sweep the frequencies. Now, if I sweep the frequencies and I will monitor what is the tip deformation, what is the tip deformation delta for this cantilever, then we can see that then initially at one frequency it will further go up. This is the first resonance, and then it will further come down, and afterwards it will again go up. This is for the second mode, and similarly keep on continues, right? So the maximum energy will go into the fundamental board and then followed by the second and third and so on and so forth. Around 80 to 90% of the energy will go into the, let's say that if you are pumping in some amount of energy to the system to undergo vibration, around 80 to 90% of the energy will go in the fundamental mode itself, right? So that's why we can see that the fundamental mode, the amplitude of vibration will always be much larger and it will be quite easy to measure as well, right? And also, whenever you go to the higher modes of vibration, the natural frequencies of the system will also further increase, right? So on and so forth. So the omega 1, omega 2, omega 3, omega 4. At the same time, now in this case, here I have a quarter harmonic. Now here I have 3/4 of an harmonic. Now here I have much more harmonics. So once I go to the higher modes of vibration, then the spatial harmonics will also increase. We do get the larger frequencies and we get the larger spatial harmonics in the system. So whenever we want to take up any of the resonance sensors, one need to look at it not only the stiffness, you need to even evaluate the effective mass of the system. And then the quality of the resonance. Now, I said any of the resonance system, we do get a resonant response like this. The sharpness of this resonance is indeed measured by what is called the quality factor. So, which is the ratio of the omega n to the bandwidth omega n divided by delta omega is basically the quality factor. That's what is basically written. This sharpness of the resonance is basically given by the quality factor. This is also a measure of damping present in the system, which is, you can say that this also equals to 1 over 2 theta. This will, the damping present in the majority of the micro scale structures will be either in the form of a squeeze film damping or in the form of a slide film damping. What is that squeeze film damping, slide film damping? Whenever you take up a micro scale structures, we have a top plate and we have a bottom electrode. And in between the two, we have a thin film of air which is trapped between the two. Right? So when this thin film, when this undergoes by, when let's say that the top plate will come below this, then what happens? It indeed will compress the thin film of air and air would like to escape out. On the other hand, if it goes up, then what happens? The air will tend to enter in. And during the process, let's see that This is basically air film what I have, and this is my top electrode. This air film indeed will exert a force back onto this structure, and this force is basically the damping force, right? And this is basically what we, since we are squeezing a thin film of air, that's why it's also called the squeeze film damping. And the squeeze film damping is a subject by itself. There are plenty of cases on the squeeze film damping. And whenever you want to realize the micro scale structures, let's say if I want to realize it by the surface micromachining, indeed we do require the edge holes for this. Why do we require the edge holes? So that the etchant can enter in and it can remove the oxide layer below this, right? And what is the advantage of the edge hole? So that the air is not just escaping out from the side, air can escape out even from the holes as well, and that will indeed will reduce the damping present in the system. So the edge holes, that's what the requirement of the holes, it has been mentioned here, right? The edge holes, the major requirement of the edge hole is for the etching purpose, but the added advantage is reduction in the reduction in the damping or the increase in the quality factor. And there are other sources of losses as well, because whenever you take up any of the electromechanical system, it's not just the mechanical system, even the electrical systems will also come in. There will be losses from the ohmic losses will also there, even the electrical radiation will also lead to the losses present in the system. Now, let us look into how we can look at the electrostatic based sensors and actuators. Right? For example, now we should start with the basic capacitance formula, and we shall go ahead. Right? Now, whenever you take up in electrostatic based sensors or actuator, they will basically be existing in two configuration, either a parallel plate configuration or a comb finger configuration or an interdigitated finger configuration, right? These are basically a parallel plate configuration, right? Let's say that A is the area of the plate and D is the distance, then this is A epsilon naught divided by D, all of you are quite familiar with it, right? Now, on the other hand, since this resembles our fingers and this also resembles the combs, that's why it's also called a comb fingers, right? Now, in this case, we do have a movable set of comb fingers which are attached onto these beams. This is my proof mass, and this is basically a movable set of comb fingers which are attached to this proof mass, and we have a fixed set of comb fingers which are attached onto the substrate. Whenever this proof mass will undergo motion, then this movable set of comb fingers will move, which further lead to the change in the air gap between the movable set of comb finger and the fixed set of finger. One side there is an increase, on the one side there is a reduction in the air gap, other side there is an increase in the air gap. In this case, you need to take into account of differential capacitance change. Right? Now, this is the first case. This is the one, this is the case for an accelerometer or the microphone you can think of. Pairing, this is the case of a parallel plate capacitor, right? As I mentioned, we can have it like a parallel plate capacitor configuration. This is the case of a parallel plate capacitor. And here I have, this is my bottom electrode and this is my electrode line. And this is a bottom electrode line. And this is basically, or whatever you can see within these holes, I can see the bottom electrode, right? And this is basically a beams which are anchored onto the substrate. And this is my substrate, these are anchored onto the substrate. And this is a proof mass, this is a perforated proof mass, right? This is a perforated proof mass. On the other hand, one can even well have a comb finger configuration or a comb drive capacitors, right? So these are basically fixed set of foam fingers, and these are movable set of foam fingers. One is I have fixed set of foam fingers which are attached to this, and other one I have a movable set of foam fingers attached to the proof mass. So whenever I have a parallel plate capacitor, now we know that the capacitance of a capacitor is given by A epsilon naught divided by B. Now, if I want to know, this is by neglecting the fringing field effect, one can even well take into account of fringing field effect also, right? Now, I will come to that, how we can take into account of the fringing field effect very short. Now, one can realize it by the fabrication process, like the surface micromachining, right? For the surface micromachining, what we do is that we'll start with a single crystal silicon and we oxidize it, we will pattern it, and we will deposit the polysilicon, and we will strip away this oxide layer so that I will get the cantilever beam like this. On the other hand, I can go by the bulk etching as well. What I can do is that I can basically do the bulk etching of the silicon, and here also I will do the bulk etching of the from the top until the desired wafer thickness is achieved. The top side bulk etching is basically meant for giving the gap between the top electrode and the bottom electrode. Now, I am going to flip this and bond it onto the second electrode. Now you do the anodic bonding and you bond it onto the second electrode so that you will basically form a capacitor between the top plate and the bottom plate. So what are the different forces which act on any of the capacitive-based sensors? As we know that the stored energy is basically half Gb square. Now, if you have the stored energy, then the force is basically stored energy divided by dou U divided by dou G will be the force along the gap direction. Sorry. And the capacitance of the capacitor is basically this. So if you take up dou U divided by dou D, you can see that you will basically get minus half epsilon V squared divided by D squared. Now, if you look at the pros and cons of the capacitive-based actuators, so almost majority of the actuators, what you can see, will be by the capacitive means. They usually require very low power and the actuation voltage is very, very small, right? And the speeds of operation is also quite large, right? They are very high speed, right? What are the cons associated with it? But if you look into the force and the distance are inversely scaled. If you go back, you can see that the force is inversely proportional to D, right? Since they are inverse proportionality with respect to the gap, we do require very, very small gap between the two plates. So that is another fabrication. Whenever I told you in the first class, whenever you have some intuition in your mind, there are always the fabrication constraints associated with it. So please keep that in mind. And whenever you want to have a very, very small gap of, let's say, 1 micron on that consideration, then what happens? There are, even if there is a tiny bit of dust particles which in, then this indeed may lead to stiction problems, right? So then your devices, the cleaning, we do require a very, very clean environment for this. But at the same time, the sensitivities are quite tremendous. Right? For example, you can take an example of a capacitive-based accelerometer. This is proof mass is micrometer square. Okay. Now we can figure it out, right? What we need to do is that in this case, we need to first evaluate. We have the dimensions of the proof mass. We already have it with us. Once we have the dimensions of the proof mass, we need to know that force is basically mass times acceleration, right? First in the fundamental step, is to evaluate what is the mass of this, and you apply force equals mass times acceleration. Note that in this case, the anchor is over here. It is like anchor is over here. So if I'm going to pull this up, then what happens? Then here there is a increase air gap. On this side, there is a reduction in the air gap. So okay, in this case, you need to take into account of the differential capacitance change, right? Please keep that in mind. So if you go forward for the analysis in electrostatic actuator, so we know that if I'm going to take up two plates, if G is the gap between the plates and L is the length of overlap, W is the width of overlap, then the stored electrostatic energy is basically what? Half CV square. C is basically A epsilon by G. Then the force along the length direction, if I want to evaluate, is basically dou E divided by dou L. That's the force along the length direction. Similarly, that along the width direction is dou E W divided by dou W. That's basically what we need to take up this expression, take the derivative with respect to width, then I will get half of L epsilon naught divided by G times V square. Similarly, if you take up dou E divided by dou G, then you will basically get force along the gap direction, which comes out to be half of A epsilon naught by G square times V square. Note that if in this case, if I'm going to take a G gap and then the electrostatic force, if I'm going to plot it up, I am basically get it out like this. The gap is very, very small, then your electrostatic force is huge, huge for a given voltage, right? So as to even either you want to use it in an actuator application or you want to use it in a sensory application, you need to design this gap, but at the same time, the gap is dictated by the fabrication. Please do keep that in mind, right? So if at all you want to know about what is the optimum gap for your case, you can go to this science foundry. This is basically this. I hope you can see the screen. This is basically from the science foundry, and you go to the silicon and insulator SOI process. And here, what are the dimensions you are going to have for the each and individual layers? And what are the design rules? Your design rules will basically will tell you what is the maximum gap that you can have. Everything is basically given over here. Please do look into what are the different things. The SOI spaces in the trench, SOI futures, right? Each and everything is clearly minimum future size is what? Everything is clearly mentioned. Please do look into the all these dimensions carefully before doing your design. And whenever you take up any of the MEMS device, in the MEMS device, what we have is that we have a top electrode and we have a bottom electrode. And top electrode is what basically is the structure which is basically suspended with the help of set of beams. Right? Proof of suspended with the help of set of beams. So it is like a proof mass sustained with the help of set of beams. That is my top electrode, and here is my bottom electrode. Let us say that I am going to apply a voltage V between the top electrode and the bottom electrode. So if I want to basically represent as a lumped parameter model of the same, then what is it? So in case of a simple electrical ones, you will see that it's basically a top electrode and bottom electrode. So once I basically apply a potential, then the charges gets accumulated, and this basically forms a capacitor. That is what is basically a simple capacitor. But in this case, since this indeed consists of beams and there are elastic members, so instead of having like a simple capacitor, this indeed comes out to be a spring-loaded capacitor. right? So whenever you take up a capacitor, we just derive the expression for the electrostatic force. Whenever you apply a voltage V, then there indeed will be electrostatic force, and from the electrostatic force, it indeed will pull it down, right? The electrostatic forces will basically pull it down. On the other hand, when it basically pulls down, the spring gets elongated and it wants to restore it back to the equilibrium position. So the spring force will basically act twice. So if you take the static equilibrium for this, you can see that the spring force equals to electrostatic force is a static equilibrium conditions. So which is basically a cubic equation. So if you solve the cubic equation, you will basically get the three roots, right? So what are those three roots? So this is basically my electrostatic force will basically scale like this. So if I'm going to take up two forces as a function of x, so this is basically my spring force, which is basically proportional to x, which will be a straight line, and other one is an electrostatic force. So both of them is going to cut at these 3 points. These are the roots of that equation, three solutions of that equation. So if I'm going to take up the same thing from the energy side, so the total potential energy will be that from the spring, that's a half kx squared, this is half cv squared, right? So there's a total potential energy what I get. Now, if I'm going to plot the potential energy, so the potential well will basically come out like this. So if I'm going to take up any particle over here, so it will come and drop at this point, and whereas if I'm going to take up any particle over here, it will basically come and fall over here. On the other hand, if I'm going to take up a particle at this point, then if there's a tiny bit of perturbation towards the right, then what happens? It will go and fall onto a value. That is why this indeed is my unstable equilibrium position, and this is the stable equilibrium position. On the other hand, this also, if you take it up, as whether you take up a point over here, whether you take up a particle over here, this indeed will come and fall onto this. So you do get two stable position and another unstable equilibrium position. So how do we check this out? Whether you have the potential energy, whatever expression you have written it right or not, you can take up the derivative of the potential energy. You will again get back this equation, right? So how do we check whether stability of your system? Stability will be you take up the second derivative of a, right? If you take the second derivative of the potential energy, this is what you get. That's k minus a epsilon naught v squared, and you put it out to it goes to 0. Then what you would get it out is that k to be equals to a epsilon naught v squared divided by g naught minus x whole cube. That's what you get, right? So this is basically a potential energy, whatever you have. Now, if I increase the potential, you can see that if V1 is greater than V2, which is greater than, sorry, less than V3, so at one in particular value of voltage, you will basically, you can see that at G naught by 3, it will be undergoing asymptotically, it's going to touch you, right? So in the earlier positions, we had it like one stable, as unstable, another unstable position. On the other hand, if I increase the potential, then my potential well will also change. At one particular value of potential is going to asymptotically come like this. And if I'm going to increase the potential further, then what happens? It will basically come out like this. So whether you take up a particle here or you take up a particle here, it will go and fall onto a value, right? So the condition of the critical stability is this, right? So from this, you will basically get v square to be equals to this. And if you substitute back into the first equation, what we got, kh equals to spring force equals to electrostatic force, then you will basically get this expression. You basically put up this v square into this. You will end up with this. From this, you get x to be equals to g naught by 3. That's what we got graphically as well. Now, if you substitute x equals to g naught by 3 into this expression, then you can get the pulling voltage expression, which comes out to be pulling voltage equals to square root of 8k g naught cube. divided by 27A epsilon naught. So what does this pull-in voltage mean? So pull-in voltage basically tells us that this is that particular value of voltage, was that particular value of voltage, because once we saw the forces, right? This is my spring force, this is my electrostatic force, right? This was my electrostatic force. So if I keep on increasing the value of potential, then my electrostatic forces will further increase. At one value of potential, this electrostatic forces will asymptotically touch this. And this is my G by 3, the deflection, right? And the voltage corresponding to this is my pulling voltage. So in this case, my spring force and electrostatic forces both are equal. And if I'm going to increase a tiny bit beyond this pulling voltage, then what happens? Immaterial of the value of the gap, my electrical forces are overtaking the mechanical forces. If the electrical forces overtake the mechanical forces, what exactly does it mean? So this is basically my electrical forces and this is my mechanical forces, right? So this is a tug of war which is taking place. One side we have a very, very strong member who is pulling it down. So it is just like since it is pulling it down, so it is pulling in. That's why it's called a pull-in effect, and this is also called the pull-in voltage, which is given by square root of this much, right? So that's what you can see this as well. So if at all at pulling, the deflection is G naught by 3 and the air gap what I get out to 2 G naught by 3. If it is beyond pull-in voltage, then it is going to snap onto the bottom. And on the other hand, one can even will get the pull up voltage, for which we would require a dielectric material. So if TD is the thickness of the dielectric material, then the pull up voltage is the pull-in voltage is given by this, and the pull up voltage is given by this. The details you can always go through the Prasanna Suresh book, or if you wish, you can always write back to me. I can even will send you the derivation. That's not a problem, right? On the other hand, if it is a simple structures like this, you can even go forward for this. Or in general, whenever you take a beams, right? Then what happens whenever you apply a potential? It is not just that you get a parallel plate motion. Then in this case, there will be a deformation. Then what happens? Your electric potential, the electrostatic force is a function of X, right? So when the electrostatic force becomes a function of X, you need to take that as well into the account. And also, in case of beams, yes, beams are also flexible elements. We need to take into elasticity of the beams, and we need to take into the bending of the beams also. If at all, where during the process, the residual stresses are inherent, you need to take into account of the residual stresses also during your modeling. And also, one can even well need to take into account of bridging field effect and cordon effect can also be included. So what are the implications of the pull-in? Pull-in is a very, very important thing. So one can make use of the full, one can't have the full gap motion, or one can even will get the full gap motion by controlling the things. And this electrostatic micrometers, indeed, they require the tuning also. The tunable capacitors can be done. That's also can be done quite a lot with the help of this pulling effect. And this is how can we counteract the pulling? For example, let us say that if the electrode is placed over here, then what happens? We know that we get a maximum deformation at this point. Then naturally, it will undergo home, right? Whenever if this G naught by 3 is a gap, you will get the pull-in. On the other hand, if at all, in this case, you can't get full gap motion. On the other hand, if at all you wish to get the full gap motion, rather than patterning it over here, you pattern it somewhere at the intermediate position, then in such cases, you can get the full gap motion. This is another example of even evaluating the pulling voltage and what would be the deformation of the different potentials you can evaluate. This is basically like a two guided cantilevers. You can evaluate the stiffness first. Upon evaluation of the stiffness, this is what you get. And after evaluating the stiffness, you can obtain the pulling voltage by square root of 8K G naught cube divided by 27K epsilon naught, or you can even well evaluate it like this also. There are several ways of writing the same formula. Then you can see that the pulling voltage comes out to be 0.25 volts. Right now, if the applied voltage is 0.4 volts, since it is greater than the pulling voltage, then naturally you will get the complete deformation of the structure. Right? Then what would be the deformation you will get once you get apply around 0.2 volts? Then it basically comes out to be a cubic equation. Then you solve for it. Then if you solve for it, then you can see that you will basically get 3 roots for the cubic equation. So these two are actually, this is not into 10 to the power of minus 6. This is 1.2 micrometers and 2.5 micrometers. Everything is in my meters only. And other one, because 1.2 micrometers is also infeasible, because 2 by 3.66 is the maximum deformation what one can get. One can't get 2.6, 1.2 micrometer deformation. Or 2.5 is also impossible. So only possible solution is this, right? So, and also if you apply around 2.24 gauge, so you can see that you will get around 0.54 micrometer. So even if it is tiny bit of voltage less than the pulling voltage, one can even well get the required deformation. If it is at the pulling, it's around 1/3 the area. And one can even well get a tunable micrometers with the help of the pulling voltage also. Usually doing this micrometers, you can even well get the tilt angles of ±10 degrees. These are like whatever the DMBs, in the majority of the DMBs, which are even well used in that is the projectors, all those things. They indeed make use of the micrometers, right? So these are DMBs. Here you can see we have the bottom electrodes, basically a CMOS substrate. So if I apply a potential between the top electrode and the bottom electrode, indeed we do get around 10 degrees plus or minus 10 degrees in the respect. And that was a case of a parallel plate capacitor, and the other cases will be in the comb finger configuration. So in case of comb finger configuration, we have a fixed set of comb fingers, and we have a movable set of comb fingers attached to the proof mass. Right? In case of comb finger configuration, we get a lateral comb fingers wherein the capacitor gets formed across this face. Right? You can see this face, right? So the capacitor basically gets formed across this face and also across this. Right? So we do get a change in capacitance between this and also across this. This is basically a lateral case. So if you evaluate the capacitance of a capacitor, this basically, if x naught is the length of overlap, if x is the deflection what you get out, then the new total capacitance comes out to be your Cp, the parasitic capacitance, plus your 2 times, this is the epsilon naught into whatever is the thickness of your structure times x plus x naught divided by t, right? And we have n such comb fingers. We have n to be equals to 4 in this diagram. We have 4 of them. So we will basically get 4 times this, right? So 4 times you are, because each comb finger, if you look into, we have 2 capacitors which gets formed. One capacitor over here, another capacitor over here. That's how we get this term 2 over here, right? And this will be the total capacitance which comes up. This is C plus C, P for each one of, right? And then this is half CV square, which all of you are familiar. On the other hand, one can even well get the transverse capacitor. Usually you do get this transverse capacitor many a times, because this indeed will give you better sensitivity in contrast to a lateral one. Now, in case of transverse, you can see that this is basically undergoing a motion sideways like this, and there is basically a change in the gap. There will be a change in the gap. In the previous case, there is a change in the area of overlap. In this case, there is a change in the gap. Please keep that in mind. In this case, there's a change in the gap. one side there is an increase in the air gap, on the other side there is a reduction in the air gap. That is the change in the left side, change in the right side. So sum of both of them will indeed gives me the total capacitance change under consideration. So this is basically an analog devices accelerometer, which basically makes use of a transverse point fingers, right? So wherein the structure is basically made out of is basically a proof mass, central mass, suspended with the help of beams. And whenever there is input acceleration coming up like this, coming up along the y direction in this case, then what happens? This proof mass will basically undergo motion, which is sensed with the help of, so these two fingers will basically undergo motion like this, sorry, not this way around, on this way around, the two fingers will basically undergo motion. So there is a change in the air gap between the two, so which further will be sensed across the two fingers with the help of this transverse two fingers under consider. This is the same thing, nothing different in this. So in this case, I have several of them. This is basically connected to the proof mass, and other one I have it the fixed set of fingers. So in my case, this is moving like this, so we do get a change in the air gap. And then these comb fingers can be even used in plenty of other applications. For example, the Sandia Labs has even well developed by the help of this basically the comb fingers, or even well driving these gear trains, gear and gear trains. Whenever you apply a potential, then what happens? There will be a motion of the comb finger, which further lead to the motion of these lever arms, and this lever arm will further lead to what? The motion of these gears and gear trains. When there is a motion of the gear trains, then this will further actuate another set of two fingers, right? And at the same time, we do have these gears and gear trains, which can further, with the help of rack and pinion arrangement over here, this can make the optical shutter to either open or close. Depending upon the applied voltage, we can either open or close the optical shutter. So one can convert the translatory motion into a rotational motion. You can realize all these structures with the help of the SOI process. That is possible. And then this is another case of a position limiter, wherein we again make use of a comb finger configurations, right? So there are plenty of applications of the comb fingers, and one can even well design a sophisticated gears and gear trains. That's also possible only with the help of micro and nano scale. And this is also can be micro motors can be easily realized. Wherein in case of micro motors, you look at this operational principle. So we do have a misaligned arrangement. Let's say that if I'm going to apply a potential across A, then it is going to rotate and align across A. Now I am going to apply it across C. It will align across C. Now I apply across B. It will align across B. So it will keep on rotating. If I just switch it from A, B, C, E, B, C, it will keep on rotating that way. And if at all you want to go forward for a high aspect ratio structures, in such cases, your SOI process is very, very handy. And also, in majority of the high aspect ratio structures, we indeed go forward for the DRIE process, which basically corresponds to deep reactive ionometry. Whenever we want to realize in a majority of the inertial sensors, we indeed want in a very high aspect ratio structures under consideration. And there are plenty of some variations you can get around the large angles. If you want to have even the linear movements, the consideration you can get out. And last but not the least, the resonance sensors, right? Whenever you take up any of the resonance systems under consideration, whenever you the simple harmonic oscillator, which one can do a lumped modeling like a spring mass system, And let's say that if I apply a harmonic load F, then what happens? Then the structure will basically will move along this. Let's say X to be the deformation, then one can write the Gaussian differential equation of motion as mx double dot plus kx to be equals to F, right? Now it will keep on oscillating with respect to equilibrium position. Now when omega, in this case, omega square will be equals to k by m, and if I just substitute, it will if x equals to x sin omega t, then I can even will get out to be x double dot plus omega square x to be equals to 0. If I compare across these two, I can write that omega square to be equals to k by m. The same thing I wrote earlier, omega n to be equals to square root of k by m, where what omega n is basically called the natural frequency under consideration. On the other hand, in general, whenever you take up any other system, in general, anything and everything in this world is not just a string mass system. It indeed has some dissipation associated with it. So that is where this damper term comes into picture. Wherein the governing equation of motion in that case comes out to be mx double dot plus dx dot plus kx to be equals to f of t. This is basically by representing it as a 1 degree of freedom system, where C is basically a damping present in the system. So, as long as we can represent it out as a simple 1 degree of freedom system, this expression goes true. If at all the complexity is further fixed, you can always make use of the FEA analysis and improve it. Like console multiphysics or any of the FEA tools, and you can always do it. Now, if you look at the dynamic response of this, if you solve that equation, then you will basically get the natural frequency to be this. And the amplitude of vibration, if I keep on increasing the frequency, this is how the frequency response looks like. Now, then the amplitude of vibration basically comes out to be f by root of k minus m omega square whole square plus c omega whole square, where k is the stiffness, m is the mass, and c is the damping, and omega is the excitation frequency. Now, here if you see, if omega is very, very small, in that case, what happens? Then omega square and omega to the power of 4 terms are very, very negligible. Then this term comes out to be just f over k. So that's why very low frequencies is completely dictated by the stiffness present in the system. On the other hand, when omega becomes equals to omega n, that means omega k minus m omega square goes to 0, right? So this quantity goes to 0, so this comes out to be f divided by c omega. So this is dictated by the damping present in the system. And the third portion will be what? When omega is very large, then m omega to the power of 4 to be much larger than the other term. So the last term will be completely dictated by the inertia present in the system. Right? So the entire spectrum, I can divide this into stiffness, damping, and inertia dominated regime. Right? And then the quality of this resonance is indeed given by omega n divided by the bandwidth. That's delta omega. Delta omega is maximum amplitude divided by 3 dB frequencies. This is also will be equal to 1 over 2 zeta. The quality factor is indeed a measure of damping present in the system. Now, if you take up any of the MEMS gyros under consideration, MEMS gyros basically consists of proof mass suspended with the help of set of beams, and we are going to drive it with the help of dry circuit. Dry circuit can be with the help of electrostatic, or usually we'll be driving it with the help of spoon fingers, so that we get a large amplitude deformations in the drive direction. And when there is an input signal, that's an angular rate signal, then what happens? Then there is a change in the capacitance. Sorry. What happened? When there is an input angular rate signal coming up, then what happens? Then there is a Coriolis force. Coriolis force acts in a sense direction which is orthogonal to the input direction on the drive axis. So that's basically angular rate will give us to the Coriolis force, which is sense by the sense direction by making use of the sense circuit. It could be piezoelectric, capacitive, or optical. In your process, in the process, whatever we are following, in the SOI process, we can't go forward for piezoelectric patterning. We can go ahead with the capacitive sensing. Right? So this is basically driven in the right direction, and then whenever there is a motion sense direction, it is sensed by the capacitance chain. And here you can see when there is a perfect match between the drive and sense mode frequencies, we get a maximum amplitude of vibration in the sense direction. On the other hand, when there is a huge mismatch between the drive and sense mode frequencies, then we get very less amplitude of vibration in the sense direction, right? But the bandwidth will further improve. So there is always a trade-off between the bandwidth and sensitivity of mini gyro under consideration, right? And these are basically a governing what when V drive is the velocity in the drive direction, then if omega is the input signal, then the Coriolis force is basically given by 2m omega crashed with the drive velocity. Note that your Coriolis force is orthogonal to your the omega and the velocity in the drive direction. And these are basically the two resonators. One is in the drive direction and other one is in the sense direction. So this is basically the amplitude of vibration in the drive direction, right? This is basically we are driving it with the help of the comb fingers. I'm going to drive it. Let's say that I'm going to apply a sinusoidal excitation. Since it is a resonant sensor, so I am going to operate it at its resonance, right? So this is basically amplitude in the drive direction, what I'm doing, okay? Now, when there is an input angular rate omega, it indeed will create a Coriolis force, which is what, since AD is the amplitude, then what omega d AD will be what your velocity. So 2m omega crossed with the linear velocity is this, right? So that will be the Coriolis force, which will act in the sense direction. So from this, you can evaluate what is the sense displacement. That again goes back to this expression I had written it earlier, which is this. From this, we are obtaining all of them, right? And once we look at this, we can see that whenever there is a perfect match between the drive and sense mode frequencies, we get a maximum amplitude of vibration, sense direction. That means to say that whenever you want to design any gyro under consideration, ensure that the drive and sense modes are as close as possible. And at the same time, if at all you want to look into but in this case, note that the bandwidth comes out to 0. Bandwidth coming to 0 means it can't measure the sudden changes in the input angular rate signal under consideration. So if your application is to measure the sudden changes in the input angular rate signal, then you go forward for a wide bandwidth. But at the same time, if your application requires huge sensitivity, then you would go ahead matching of the then I'll give you some of the examples. Here is basically which we are realized with the help of surface micromachining. These are basically the natural frequencies in the drive and sense direction. I am basically actuating the drive direction with the help of sensors, and I am sensing it with the help of parallel plates in the sense direction. So I am basically operating in a push-pull what in anti-parallel mode of vibration. Why do I operate in the anti-parallel mode of vibration? So as to ensure that I will be cancelling out the linear component of acceleration. Because we know that linear component of acceleration is much larger than the Coriolis component of acceleration. Somehow we have to cancel out. That is why we indeed will operate in a anti-parallel mode of operation. And when we fix up the Coriolis force, which is basically sensed in the sense direction, it is sensed with the help of a parallel plate capacitor. Again, there could be another change wherein we can have several designs as well. Here you can see that the drive and sense modes are quite close by, and there can be another design as well wherein we get a perfect match with the drive and sense mode frequencies. So we have seen three designs right? One that all three are tuning fork gyros, and we can see that there are one case there's a perfect match, and the other case there's a huge mismatch, other case there's a small mismatch. Let's see what would happen. In this case, even if it's a single mass, you can see that both drive mode and sense modes, they are completely decoupled. So whenever you want to design a gyro, you need to ensure that drive and sense modes are decoupling. Decoupling of modes is a very, very important parameter, right? So, for example, so these are, I think, you know already. I have discussed this, so I'll skip this. But this I didn't mention. Please keep this in mind. Whenever you take up a guided cantilever, the effective mass will be around 13 by 35 times the total mass. On the other hand, it's a simple cantilever. It's around 0.24 times the total mass. Simple cantilever is this. On the other hand, guided cantilever is. And in your case, let us say you are having some objective in your mind, then your stiffness is basically dictated by your beam geometry, and the effective mass is dictated by your proof mass, and of course, to some extent from your piece. But the majority will be given by your proof mass. And what the quality factor of your system will be dictated by what? Now, of course, by the operating pressure, because operating pressure intake will tell us about what is the number of particles we have in the system. So that will indeed dictate the quality factor. And of course, sense capacitance gap will also dictate the quality factor. And the sense capacitance gap is indeed dictated by the DRE aspect ratio. So in your SOI process, please look into the aspect ratio, which I will discuss it during the fabrication session. So you can always do the back calculations and evaluate, and you can, this is basically I have back calculated and evaluated for the Z-axis gyro under consideration. And you can do the numerical modeling either in ANSYS, Coventry, or Thomson multiphysics, anything under consideration, and you can come out with the designs as well. And whenever you think of a gyro design, in this case, we need to do the home finger design as well as the sense design, because we are driving it with the help of comb fingers. So for the comb fingers, again, we need to look into what is the comb finger gap, what should be the comb finger length of overlap of them. In this case, I told you in the earlier slide, we need to consider the fringing field effect. So if at all you want to consider the fringing field effect, there will be another 14% increase in the effective force, what you get it out. That is what is 1.14 time coming over here, right? And also, I told you that you will make use of you will always operate it in a anti-parallel mode of vibration. How do I operate in the anti-parallel mode of vibration? So as to operate in the anti-parallel mode of vibration, we will basically make use of a drive circuit, which is also called a push-pull driving mechanism. In case of push-pull driving mechanism, here I have basically VDC plus VAC, and here again I have VDC plus VAC. Here I have phase shifter, so I will get VDC minus VAC over here. So it will always undergo push-pull driving under consideration. So I will cancel out the linear component of acceleration. So the total force, what I get out will be this. So similarly, for the bottom electrode design also, you need to do the back-end calculations and see what would be the base capacitance, you get it out, and then the change in capacitance, what you get it out. And then for the drive direction and sense directions, you need to evaluate the damping. The drive direction, it's most of the time will be dictated by the slide film damping, and then the sense direction is dictated by your squeeze film damping. And if at all you have the comb fingers, you can even well get the squeeze film damping in the drive direction as well. And you can even well develop a completely a Simulink model, equivalent Simulink model. If you do anything in either console, Coventry, or anything, it will typically take around 2 days or 3 days. But if you do all the back-end calculations and come up with a model in Simulink or MATLAB, you can do it everything in MATLAB and Simulink environment, and you can develop your entire model, and within a few seconds you can get the results out, right? So this is a complete model what we have developed for the gyro. This is basically for the driving, and this will give us the drive velocity, and if you integrate the drive velocity, it will give us the drive displacement, and then which will basically omega 2m omega times this drive displacement will give the Coriolis force, which will act in a sense direction, which will basically use me the sense displacement. From this, you can evaluate what is the capacitance change. Okay, so here you can see that in the first design, since there's a huge mismatch, we get the output follows the input, whereas in the second design, since the mismatch is very, very small, the output is not exactly following the input, whereas in the third design, output is not at all following the input. So in this case, you get a excellent sensitivity, but the bandwidth is 0, right? So that's why there's always a trade-off between the bandwidth and sensitivity. So one can now get with plenty of other designs of the gyro. This is another design of a unique fork gyroscope. This is a case of a vibratory ring gyroscope. This is a case of a dual axis gyro. This is also a dual axis gyro. This is also another tuning fork gyroscope, right? This is another set of VRG, you can get it out, right? Here, this VRG, we can realize it with the help of your SOI process. This is also, we can realize it with the help of the SOI process. This here VRG also, we can realize it with the help of SOI process. But keep in mind the process conditions whenever you are designing it. And we can even well come up with a plenty of tri-axis designs. As a matter of time, I will not go into the details of the tri-axis gyros. How much time do I have? I'll just show this for you, how one can get this. For driving it, I'll basically driving it in the anti-parallel mode. And then whenever there is a roll signal which is coming up, you can see that there will be a Coriolis force which comes up across these two plates, which will be basically sensed by the capacitance change, right? Now, on the other hand, when there is pitching, then this is sensed by, we do get the pitch for Coriolis force across these two, then these two masses will move up, then I will take in sense the capacitance change. Now, on the other hand, when there is a yaw motion, then what happens? We do get the motion across this. These will basically experience the Coriolis force, which is basically sensed by the capacitance change capacitors which are patterned over here. So these are basically the different mode states what I have for the pitch, roll, and yaw, and they are completely decoupled. So that's what I said. Decoupling of modes is a very, very important parameter whenever you are designing a gyro. The details are already available in my measurement paper. If you are interested, I can pass it on. You can always write to me. I can pass on my paper. You can go through this. And whenever you design any structures, you please do carry out a parametric design and see that what is the optimum dimensions for your design. But whenever you do the parametric studies, please keep in mind the fabrication constraints. And also, one can even well evaluate the damping and other things with the help of numerical results also. Here also we can see at the different pressure levels, what are the damping we are getting out if it is a perforated plate, on the other hand, if it's a solid plate. And this is the case even with the help of just a cool finger under consideration. And one can even well see that as a function of the operating frequency, how the damping force will further change, and at a different operating pressure, how the damping coefficients can change. All of this you can also carry out with the help of any of the numerical tools under consideration. And one can come up with several designs under consideration, and you can make use of the Simulink model, or if you wish, you can do the complete coupled field simulations, and you can do all the detailed system level analysis for this, any of the gyro under consideration. And then you can come up with the complete performance characteristics. Okay, I will stop here. I would like to take up any questions if you are there. Yes, any questions, please?
Well, thank you, Professor Venkatesh, for the training, for all the information you gave us. I think they need some time to maybe get used to all of this information, and they can also send you an email. So all of you have the email from Professor Venkatesh, and also all the emails from the organizers in case you have any questions. So please send them to us. We will be happy to help you. In case we have no questions, thank you everyone for attending this webinar, and see you the next week on Friday, the same time.
Yeah. Okay.
So,
Any
thank you very
questions? We'll
much.
see you again in the next week. Thank you.
And have a nice weekend.
Have a nice weekend. Enjoy.
Yeah, thank you.
Bye.